Welcome to problem solving session for computational commutative algebra. I am Siddhi Balu Ambore from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 9. That is problems related to degree of Hilbert-Samuel polynomial, a dimension of Noetherian local rings, dimension of polynomial rings, and algebras over a field. So let us start with our first question. So question 1 is that we have to check the true or false that let R is equal to kxyz quotiented by this ideal xy, xz, yz. Then for every homogeneous linear form A in R, height of A is 1. Okay, this is the question. So when they are asking this, so this K is a field. Okay, let me write it somewhere. K is a field. Okay, so we have this quotient ring, polynomial ring kxyz quotiented by this ideal xy, xz, yz, and we are asked that every linear form A in R. So when homogeneous linear form. So when we say that homogeneous linear form, it means see we have this polynomial ring quotiented by again this ideal xy, xz, and yz is again homogeneous ideal, and we are quotienting it. So the resultant this quotient ring has grading. Okay, and in that we are considering homogeneous linear forms, means this R has this grading, and we are just considering element. So this A is in R1. It is of the form x bar plus by bar plus cz bar, something of this sort. Okay, so or this is very bad. So let this A is some, what to use. Okay, let me take this fx bar plus no. It should be constant. So alpha, let me take this alpha x bar plus beta y bar plus gamma z bar, where alpha, beta, gamma are from K. This x bar, y bar, and z bar are images of this x, y, z under this quotient of ring R. Okay, so I hope you understand how this looks like. So we have to check whether for every homogeneous linear form, whether height of that A is always 1 or not. So can you guess whether this will always be true given in this ring R? So note that this will not be true. Okay, because when we say height of this element A, it means we are considering the minimal prime containing this element A and then looking at its height. Okay, so height of, I mean, we can't always give information about height just by looking at the element. Okay, I mean, I'm just saying that this need not be true because we are in quotient ring. So I mean, this A might have 0 divisors and so on, which will change the height and so on. So let us consider this example. Okay, let this A be x bar. Okay, and note that we have this also. We learned this in this week's lecture, that for prime ideals, height of P plus dimension of this R mod P is equal to dimension of R. Okay, and since we have this A, This is just an ideal. This, I mean, this, when I say height of I'm talking about height of this A. So this A need not be a prime ideal. Okay, but for anything related, I mean, the height of an ideal can be looked at through the height of its minimal prime. Okay, because what is height of an ideal? It is just minimum of height of all the prime ideals which contain that ideal I. Okay, so height of this A is just height of one of the minimal primes of this ideal, this A. So from this A, I mean, for a given ideal, we can reduce that problem. I mean, when we have to talk about height of some ideal, we can reduce that problem to the height of its minimal prime. Okay, so keep this in mind. So let me just quickly write this, right? That any problem related to the height of an ideal can be translated to, I mean, not any, I mean, in most of the cases, translated to the height of its minimal prime. Okay, and once we have height of a prime, we have this identity here. Height of prime is plus dimension of R mod P is dimension of R. Okay, so we will do this. So let us consider this A to be X bar in my quotient ring R. And here dimension of R is what? Dimension of R is dimension of this ring, right? K, X, Y, Z, quotiented by XY, XZ, YZ. And what is dimension of this ring? So when we have to find the dimension of dimension of this ring, we have to find the dimension of, I mean the length. So dimension of R is supremum of, I mean, we have L such that is chain of primes in R. Okay. So when we have to talk about the prime ideals of this quotient ring, we have to check the prime ideals. I mean, we did find the dimension of this ring, I guess, in earlier case, because we have seen this ideal previously also. So if I want to find chain of primes in here, so note that 0. So correspondence between prime ideals in K, X, Y, Z and prime ideals in this ring R is that spec R is equal to P in spec S, spec K, X, Y, Z, such that P contains this XY, XZ, YZ. Okay. So we have to check prime ideals which contain this XYZ. So note that if a prime ideal contains X, then it contains either Y or Z. Okay, so prime ideals. So let us take P in spec K, X, Y, Z and such that P contains this, let me write normal P, XY, XZ, YZ. Okay. And so, and then this dimension of R mod this X R is dimension of this P. Dimension of this K, X, Y, Z, P. So this is, I am considering this P in spec such that, as I said earlier, that we can reduce the problem of this ideal to its minimal prime ideal. So I'm considering this minimal prime ideal of this R mod X, Y, X, Z and Y, Z. So I have this. So how this ring look like? So if without, So we have x, y belong to this P. So without loss of generality, we can assume, so this implies x belongs to this P or y belongs to this P. So without loss of generality, we can assume this x belongs to this P. So in that case, this K, x, y, z quotiented by this x comma y, z is isomorphic to this K, y, z quotiented by y, z, right? Now I'm dealing with this associated prime P, okay, which contains this x, which contains, let me give this ideal name I, which contains I. Okay, I have this. And once I have this, the minimal primes of this kx, kyz, comma yz is this, only y, comma z, right? Because the only prime ideals, so once a prime ideal contains this yz in this ring, let me call this A1. In this ring A1, it either contains y or z. And the moment I have y, yz belongs there, and the minimal prime is just y. And so height, these are the minimal primes. And what I can say, that dimension of this ring will be 1 because I have this minimal prime contained in this, okay, or this contained in y comma z. So when I have to look for the chain of prime ideas, this is my P0, which is contained in P1. So therefore, dimension of this ring ky comma z quotiented by yz is 1. And since these two are isomorphic, here x comma yz, I get that dimension of this k x y z quotiented by x comma yz to be 1. Okay. And similarly, when y also belongs to my prime ideal P, this similar argument can hold because they are symmetric. Not symmetric, but or anything of that. In that case, also the dimension. So dimension of R will be 1 because this was isomorphic to R. So dimension of R was this dimension of k x y z mod P. And from here we got that dimension of this k x comma yz is 1 from here. And just ignore this, we don't actually need this. Then therefore dimension of this R is actually 1. Okay, and then R mod A bar is isomorphic to this k x y z quotiented by this xy, xz, yz, and x. So and we can see that this x comma y comma z quotiented by this x comma yz. So this is equal to, and we know, so dimension of this R mod A is dimension of this kxyz, which we already calculated, x comma yz, which is 1. Okay, so dimension of this, dimension of R is 1, dimension of R mod A is 1. So therefore dimension, therefore this height of A bar must be 0. Okay, because we know this dimension of, because we reduce the problem to this height of A bar plus dimension of R mod A bar, or just A, not even A bar, is equal to dimension of R, right? And we got there this height of A is 0 because here we have height of R mod A to be 1 and dimension of R to be 1. From here, dimension of R was 1 because, I mean, if you want to see directly the height of, you can see that here the minimal primes are this x comma y. Sorry, this is the minimal primes are x comma y, y comma z, x comma z, and which are contained in this, which all of these are contained in this xyz. Okay, so height here is 1. And again, when I go mod this x, r mod x, to check the height of this element x here, I end up getting this ring when I quotient it, this ring, and height of which is again 1. So that's why directly height of A is 0, and dimension of this R mod A, this ring here, is 1, and dimension of R is 1. So that's why height becomes 0. Because from here I get, so this A1 which I wrote here, the dimension of, so height of A is actually dimension of this ring A1 which I wrote here, and which is, oh, dimension of this R mod A, which is 1. So this is 1, dimension of R is 1, so height of A must be 0, which is what gives me contradiction, because their claim was that height of A is always 1. So that's why this is false. Any doubt here? I mean, what we are doing is we are just calculating heights of element and dimension of the ring. We have done that so many times. Since this was a monomial ideal, it was easier to calculate the minimal primes in this case, because we could decompose and so on. So is there any doubt? Okay. So this was it. So height of here, in fact, this A was my x, so height of x bar is 0 here. So let us move to now second question. Let f be a homogeneous polynomial of degree d, then the degree of the Hilbert-Samuel polynomial of this power series ring. Okay, now we are in power series ring. This f is a polynomial ring. Sorry, f is a polynomial of degree d. Okay, so it's not a formal power series. It's a polynomial of fixed degree d, and we are now taking quotient by this f in power series ring k x y z. Okay, and we are asked about the Hilbert-Samuel polynomial of this quotient ring with respect to its maximal ideal. So whenever we talk about Hilbert-Samuel polynomial, we always talk it, I mean, we always find it with respect to some ideal. Okay, and here we have to find it with respect to maximal ideal. And when I say maximal ideal, it is maximal ideal then in this power series ring. Okay, this, and these are the options that it is 1, 2, see it is d minus 1. So d was this degree of f, and my last option is D. So we have to check the degree of this Hilbert-Samuel polynomial whenever I have this f homogeneous polynomial of degree D. Okay, so first let me go through a quick definition of what is Hilbert-Samuel polynomial. So let R comma M B, a Noetherian local ring. MB, a finitely generated R module. And this I is such that radical of I is M. Okay, then there exists a polynomial Pi comma M T in Qt. Okay, so this Pi comma M, so this is polynomial of with Hilbert polynomial this of this ring I mean let me just finish it, that such that for all n greater than big enough, lambda r of m mod I n plus 1 m is equal to Pi comma m n. Okay, so what we do is we take this Pim is actually lambda r of this coefficients of this. We have I mean we know how the Hilbert polynomial looks like for some module. So we are talking about it with respect to this ideal I, and we have this that lambda r of m mod I n plus 1 is Pi comma mn. Okay, and this P, then this Pi comma mn is called the Hilbert-Samuel polynomial of m. Okay, so this is the definition where, and note that here it is Noetherian local ring. We have to start with this Noetherian local ring, and note that here this kxyz power series ring is also local ring. Okay, the only maximal ideal here is, again here k is a field. Okay, k is a field. The only maximal ideal here is xyz. Okay, I mean you can check that again, because yes, I mean this polynomial ring here is not the polynomial ring here. This, let me write this, R is equal to this k xyz is local ring. You can check this, because if there is some prime ideal, uh, I mean just like what we had in this power series ring, if I have some this a into f of x degree f of x greater than equal to 1, a non-zero, then this a plus fx is unit. Okay, and then any proper ideal of this kx is of the form x power r. Okay, and then if I want to talk about maximal ideal, I mean if every ideal is of this form r, where r is greater than 0, then if I want to talk about prime ideal containing this ideal, then only possibility is having this. Okay, so that's why this is local ring with maximal ideal x, and so m spec of kx is just this ideal, but note that spec of kx is 0 ideal plus this, not plus but 0 ideal and this, because we are in integral domain. Power series ring is integral domain, we are in k and so on. So we have this information with this, and this same thing happens with the formal power series rings as well. Again, the constant plus volume, this fx, y, z, here instead of x, y, z, I will write this in here. This fx, comma, y, comma, z with degree of this fx, comma, y, comma, z greater than equal to, or let me just keep it as it is. This degree of f x, comma, y, comma, z greater than equal to 1. And again, this a plus fx, comma, y, comma, z, you can check this is unit. And then kx, every proper ideal will be of this form: x power r1, y power r2, z power r3 maybe. And then maximal ideal, if I want to talk about maximal ideal, it will be of this form. Note that here prime ideals will be this ideal generated by x, y, and z, and so on. So we will have this ideals as well. Ideal generated by y, ideal generated by z, ideal generated by x, y, x, z, and so on. But still, the low maximal ideal will be only this ideal generated by x, comma, y, comma, z in this formal power series ring. So the setup which we need here about Noetherian local ring, it is there. That's the only thing I wanted to emphasize when I was doing all this. So let us go back to this. Here we want to find Hilbert-Samuel polynomial of this k, x, y, z quotiented by f. F is a homogeneous polynomial of degree d, and we have to find it with respect to m. So again, this radical of m will be again m. So we have to find this I, m comma m, t, and so on. So let me just start with it. Please let me know if there is any doubt in the definition or what we are finding and how the given, the base conditions are satisfied to start with the problem. Okay. So let us consider this R, K, X, Y, Z. Okay. And so dimension of this K, X, Y, Z is 3. Okay. Because we have this chain 0 contained in X, contained in XY, contained in X, comma, Y, comma, Z. And we can't insert any polynomial, any ideas in between. And this is the unique maximal ideal. Okay. And so that's why dimension of this is 3. And dimension of this is 3. Also, height of this ideal M is also 3. Okay. There is no doubt in this, I hope. So let F be non-zero. And then dimension of this K, X, Y, Z quotiented by this F will be 2, right? Because we are considering this f to be non-zero and we are quotienting it by some non-zero element in an integral domain. Okay, this kxyz, this kxyz is integral domain and we are reducing it by some non-zero element, quotienting it by some non-zero element. So its dimension will always reduce. We discussed this also in the last lecture. Okay, so and we have this result that degree of Hilbert-Samuel polynomial PIMT is dimension of module M. Okay, so if I want to find dimension of this module M, Hilbert-Samuel polynomial, degree of PMT, and this is my M here, then it will be equal to dimension of this K, X, Y, Z quotiented by this F, which is 2. Okay, so that's it here. So only thing we had to check that when we quotient something with respect to non-zero polynomial, the degree reduces. And here, yes, one more thing here, the degree t must be greater than 0, because if we consider this f to be a constant, then k quotiented by this constant, non-zero constant again, will be my entire ring, because constants are units here. So in that case, this doesn't hold, because dimension of k, x, y, z quotiented by that ring will be just 0, and it will be 0 ring, and the dimension will be 0, and this degree of PMMT will also be 0 using this. But yeah, we have to consider this to have this degree of Hilbert-Samuel polynomial to be 2. Okay, I hope you understand why this degree has to be positive. Because constants have degree 0, and if I take quotient of this Rxyz with some constant C, it will be dimension of this 0 ring, which is 0 anyway. So that case is not very interesting, or we don't want to look into it. So understand that this degree of f should be at least greater than equal to 1, and we are quotienting this f, this power series ring, by this non-zero element f in integral domain. So height has to reduce, and that's why this dimension of this kxyz quotiented by f is 2. I hope this is clear. Is it clear? I hope. Okay. If you have any doubt, please write it in the chat. Okay. Otherwise, I will move to this next question. Question 3. So let R be this K. Again, we are in polynomial. So f is not equal to 0, then, so note that the dimension of this k, x, y, z is 3, and we are quotienting it with some non-zero element, right? So that non-zero element will be contained in some prime ideal. So let me just, so as we did earlier, so this dimension of, so when we take this, let me just write it down properly. Yes, so I have this element f, right? When I go this modulo k, x, y, z quotiented by this f, okay, or just consider this ring for now. The dimension of this ring will be is equal to dimension of this k, x, y, z quotiented by some p, where this p is minimal prime containing this f, right? The dimension and heights are, I mean, what I can say, we are using this in short. P plus dimension of R mod P is equal to dimension of R. Okay, so when I'm going quotient by some non-zero element, it will have some prime factor. Okay, and that prime factor, I mean, if this f is some f1 power e1, fk power ek, then this I'm writing in general. then this dimension, since f is the only, this is my principal ideal, the dimension of this k, x, y, z quotiented by this f will be equal to dimension of this k, x, y, z quotiented by this fi in fact. And now I am in quotient ring, and with this f being some non-zero element, so my what I get is here the prime ideas, my instead of starting with 0, my prime ideas are so earlier if this was my ring, this was my, what I can say, this was my chain of prime ideas contained in P, P1 contained in some PL. Now my chain is reduced, so 0 is not there, and my chain starting from here. So it is now, let me write here, Q0 contained in QL minus 1. The chains are now shifting. Okay, so the supremum which we were taking is now got, I mean, it's reduced by 1 now, because we are going, we are quotienting it by this f, which is again non-zero element in my ring. Is it okay? In my integral domain, in fact, okay? It's not true in, what I can say, in non-integral domains, because we can quotient it by zero divisor and the height will be always same. But since we are in integral domain, the height will always reduce by 1. Is it okay? Some non-zero divisor when we, is it okay now? I mean, how the height is reducing? Okay. So now let us, yes. So that's the only thing we used here. That dimension when quotiented by this f is now 2 because of this argument here, like how the height is reduced, height or the dimension of, height of the ideal or dimension of its corresponding quotient ring is reduced by 1, and that is happening here. And we use this, let me just highlight it with some other color. That degree of Hilbert-Samuel polynomial is the dimension of, is equal to dimension of the module M. And since the my module M was this, its dimension is 2. The question was asked about the degree of Hilbert-Samuel polynomial. It is 2. Okay, and what I mean, and I hope it is clear that when it is 0, it is constant and the dimension is 0 and so on. So that's why the degree has to be at least 1 for we to proceed and so on. I hope this is clear now. I mean, the question is also clear that how we are getting the degree to be 2. Okay, and note that this is like very general statement here. F needs only to be a homogeneous polynomial of degree positive, and we are getting that its degree of that Hilbert-Samuel polynomial must be 2 and so on. So let me now move to next question. If there are again doubt, please write it in the chat or unmute or let me know. Okay, otherwise I'm moving to next question. Now this x square comma xy is, yeah, x square comma xy is in, it's an ideal in formal power series ring, and so on. I mean, so true or false again, that for every linear form in which y is just a second, y is a term when they say y is a term, that means that y appears with a non-zero coefficient. Okay. Is a system of parameter. So we have to check this. Again, this R is a power series ring. It is graded. Again, we are quotienting it by x square comma xy, which is again, sorry, a homogeneous ideal. And then again for every linear form in which y. So this y, I mean what they are asking is every linear form. So again linear form. So they are saying that this fx plus by, where this b is non-zero. I mean, linear form in kx comma y will be of this form at least. With b non-zero, they say that this will form a system of parameter. Any doubts here? I mean, what the question is? So this f is forming a system of parameter. That's what we have to check. Okay, and so first we see the dimension of, so what we have to check, that dimension of this r quotiented by f is 0 or not. We saw that if something is a system of parameter, when we quotient it by those elements, the dimension becomes 0. For example, what we had, that if a1 to an is a system of, I think we used this last time also, system of parameters of m, then again these are in R, okay? Then dimension of this m quotiented by a1 to an m is 0. Okay, and that's what we will be doing. We will be checking the dimension of this f m or this r mod this element and so on. So before we move to that, let us first check what is dimension of this. We already have this, right? Dimension of kx comma y is again 2. Okay, we have this chain contained in x comma y. Okay, and this is again local ring, though we don't need here. I'm just adding. And again now this ring which we have here, kxy x square comma xy. What is dimension of this ring? So when we want to find dimension of this ring, we have to find the chain of ideals containing this ideal x square comma xy. So note that the ideal x contains this ideal, right? I mean x square comma xy, which is anyway 0 here, and also not prime. Okay, and this contains this ideal, is contained in this ideal generated by x, and I can extend this chain by this. So this is my p0, this is my p1. So dimension of this is 1. Okay, so this spec of this ring R, so this was my R here, is just these two ideals. Note that 0 is not prime ideal here because x into x giving me 0. So spec R contains these two ideals and dimension of R is already 1. So therefore any system of parameter will have length 1. Okay, using this result here, that a1 to an is a system of parameter, then dimension of m mod this a1 to an must be 0. So if I check the dimension, and dimension of this ring is 1. So if I want to have the dimension of R plus dimension of this R mod F plus this height of F and so on. So here dimension of R is already 1, and here dimension of, if I want this to be 0, the height of this, if I want to be 1, then it will contain at only one element, something of this sort. I mean, this was not very good way to see these things, but just to get the flavor, I am just explaining that any system of parameter will have one element 1, which is dimension of the ring or module. Okay, so dimension of our R is 1 here, so it will have only one element in its system of parameters. So let this F, so we have to check whether the linear forms are giving me the system of parameters or not. And here F is such that B is non-zero. Okay, that's the condition given, that every linear form in which Y is a term, that is Y appears with a non-zero coefficient. So we have to check that F, which are linear forms are of this form, ax plus by, be non-zero. Let me write this small to check, to see that these are elements in the quotient ring. B linear form, B non-zero. I mean, we already wrote, but that's okay. So now this R mod F I need to check, right? So R mod F is what? K x y quotiented by this x square comma xy quotiented by this F, which was x square comma xy. No, I want to check with respect to x plus by comma x square comma xy quotiented by x square comma xy. So this is isomorphic to this ring K x comma y quotiented by this ax plus x by x square comma xy. And now note that here this xy is here in ideal generated by ax plus by comma x square, because I can multiply this element by x square. So x into ax plus by minus a into x square, I get this by bxy, and b is non-zero, and we are in polynomial formal power series ring over a field. So this imply that this xy belong to this ideal generated by ax plus by comma x square. I mean, just understand this much for now. So this is for now isomorphic to this k x comma y quotiented by ax plus by comma x square. Okay, because this xy is anyway in this ideal generated by these two elements. Okay, this much is clear, that how this R mod F is now isomorphic to this ring. Okay, so now I do the change of variables. So I consider this. Now this, instead of x, my x is going to x here. That's not a problem, but let me just write u here. And this ax plus by going to this v here, suppose. Okay, and then how this ideal will look like here? So when I have this, my x is just u, and this y will be some v minus au by b. Okay. Then this k x comma y quotiented by this ax plus by. This will be isomorphic to this k u comma v quotiented by this u square, sorry, x square, u square comma v. Okay, because this is a linear. I mean, when we have to do this change of variables, the only thing we have to check is that this, when we shift these variables, the, what I can say, the map which we are defining, this map has to be onto this on. So this, what I'm doing here, this needs to be onto. Once I have this onto-ness, this shifting of parameter or change of variables is valid, and I can talk about this isomorphism here because of, let me call this map, the map pi needs to be onto to talk about this change of variables. Okay, and you can check that this map is onto, and I mean this, here we are in actually power series ring, but if you are not in power series ring, then there is a result that if R is the integral domain, then Rx in polynomial ring, Rx is equal to Rgx if and only if, so for some non-zero polynomial gx in Rx, if and only if gx is equal to ax plus b for some b in R, and a is a unit in R. So this is here, and when I write this v by b minus a by bu, this v by b have this form, and this b is just element. So this is like looking at this k u comma v as k u v. So this constant here is from this ku, and v is now my variable. Okay, so you can just, I mean, we don't need to do this, and just by using this expression here, we can conclude that this map is onto, and this parameterization is valid, and so on. Is this okay? So this, which when I'm doing this 1 by b into v, so this is unit anyway, because b is non-zero and we are anyway in fields, so this coefficient is not a problem. Similarly here. Okay, so we are just using this. I just want to say that this isomorphism is true. Okay, and when I work in this ring u comma v quotiented by u square comma v, what is the dimension of this ring? Here, the only dimension of this ring will be 1, right? Because, sorry, 0, because dimension, the spec of this ring k u comma v quotiented by u square comma v is just this ideal, because once Dimension of this ring means we have to find the chain of prime ideals containing this u square comma v, but u square comma v, only prime ideal containing this ideal is u comma v. So sorry, here u comma v. So this is the only ideal. So dimension of this k u comma v quotiented by u square comma v is 0, which is dimension of my this k, I think, yeah, kz comma quotiented by this f, which is 0. So therefore this f is a system of parameter, and this f was such that ax plus by, and this b non-zero, we actually needed this, okay, to conclude. Otherwise we can't say that this happens in general. We need to have this b non-zero, and once I have this b non-zero, then only I can say that this, I mean, here also if we see, this a needs to be unit here, and this non-zero-ness of this b here actually giving me the onto-ness of this map. Otherwise we need not have this map onto. And in fact, this in this case will be x going to u, and ax going to x plus by going, again ax going to, I mean, it has to go to some 1 by au and something of that sort. I hope you understand. This b has to be non-zero for this map to be onto, because then ax going to u imply that ax going to au, and this b non-zero doesn't make any sense here to change the variables or parameters. Okay, so I hope this much is clear. We just changed here the variables to arrive at this simple ring. When I say simple ring, not the simple ring, I mean the ring with simpler variables and form. And we get the dimension of this u comma v is this, and which was this isomorphic to kxy quotiented by, oops, not this, r quotiented by this f, or let me write this fr, but doesn't matter. Is this okay? With b non-zero. Okay, so since we are in monomial ideals, it is easier to find height and dimension and so on, and to check this how spec looks like. Okay. Now we'll move to next question. So let question 4. Again, true or false. So let r comma m. So when I write this r comma m like this, it means that these are local rings. Be an integral extension. Okay, so Rm contained in S comma n is the integral extension of Noetherian local rings. And let just a second. Let I be an M primary are ideal. Then this IS, that is I extension, is N primary. Okay, so this is the question. So we have this Rm, Noetherian local ring, and its extension is S comma N. So they are saying that if I is a M primary R ideal, then this extension of this ideal I will be n primary S ideal. Okay, so this is the question asked. And when, so I extension is n primary means radical of I extension is m. We can do this because we are, we have this m as a prime ideal. It's not n. Okay, in case of maximal ideal, this happens. But in general, uh, n is some k primary, not k. I mean, if n is some ideal, I is some p primary ideal, its radical need not be that p. We have seen that example. I mean, look at this ideal itself, xy. Okay, this ideal I is also xy primary, right? Because it's what, x square intersection x comma xy. Sorry. I hope x intersection x square comma y. Okay, and here this ideal I is also xy primary, but its radical, if you see, radical of I is only ideal generated by x. Radical of I. So when I have radical of I to be maximal ideal, then this happens. I mean, I hope you understand, like, since we are talking about only maximalness, this happens. So first of all, note that this I extension, sorry, I is M primary are ideal. And this, note that this I extension is a proper ideal. That is, this IS is not equal to S. Is this happening here? Can we say that this is always true? Just because we have ideal here, this IS need not be holding. I mean, the IS, when I take the extension, I take the ideal generated by this image of I in S. And I'm saying that this is not the whole ring S. Can we say that? Okay, we need to actually show this, okay? Otherwise, we can't proceed with saying that it is N primary and so on. So this is true because if IS is equal to S, then since we are in naming R is Noetherian, R comma S Noetherian, if IS, we don't need Noetherian, is it? This implies S is a 0, which is not true, okay? We are working with this non-zero rings. R is contained in this S and so on. M is maximal ideal. in R, which is again non-zero, contained in S, and so on. So this is not true. So IS is definitely not equal to S, okay? If by Nakayama. To have the Nakayama, we actually need to have this I to be contained in, so these are S is local ring. So only the maximal ideal is N, and any proper ideal in any ideal in I will be contained in that maximal ideal N. So this IS is equal to S. I mean the Jacobson radical condition which we need to have in order to apply Nakayama lemma. That this IS or I extension is not a prime, not the whole ring, because we have to start with producing some ideal which contains this I extension, so that we can arrive at the conclusion. Okay, then this I extension contraction will be contained in I contraction. Okay, contraction follows the inequality. Okay, so but we know that for any ideal I is contained in I extension contraction. You can see this. This is quick check. So I have this I contained in I extension contraction contained in this Q contraction. Okay, so if I take radical, then radical of I is contained in I extension contraction, radical of this Q contraction. Okay, so but radical of I is this maximal ideal M, and Q contraction will be a prime ideal because Q was prime ideal. Q contraction will be prime ideal, and its radical will again be a prime ideal, right? So Q contraction, so M will be contained in Q contraction because since Q contraction is prime ideal, therefore radical of Q contraction is again prime ideal. So therefore this Q contraction must be M, because we started this Q with the spec of S and we contracted it in here, which was again a prime ideal. So this is prime ideal. So we have this, that R mod Q contraction contained in S mod Q is finite or integral. So this S mod Q, but this is filled. So this imply my Q, this implied that S mod Q is filled. This implies that Q is maximal ideal, but S is local ring. So this implies this Q is actually N, because this implies Q belongs to M spec S, which is only this ideal N. This implies this Q is N. Okay, so therefore radical of I extension is actually here. From here we have this radical of I extension is, see, it's actually n. Is this okay? We just started with some ideal I and arrived at this I extension is contained in some prime ideal, and we got that this prime ideal is the contraction of this prime ideal is actually a maximal ideal, and we have this that if, I mean, this is a result from earlier classes, earlier weeks, that if our, I mean, in fact, we also proved this, if you remember, that this, if some ideal is lying over in the, I mean, if R is inside S and it's some ideal Q is going to some Q extension, then R mod Q is filled if and only if R mod Q extension is a field. I think we did this type of question in earlier lecture, if you remember. But apart from this, we need to check that I extension is not a whole ring and it is a proper ideal. And we got this because S is a Noetherian ring and if it is equal to S, then S will be 0, which is not true in our case by our assumption and using Nakayama lemma. And then I extension, we assume it to be contained in some Q, and I extension contraction will be contained in Q contraction, which is prime ideal, and this is general identity for any given ideal, and we use this to arrive here, and we get that this M is actually contained in Q contraction. And then Q contraction is actually ideal M, and then we get that this Q radical of this I extension is actually N, and therefore this I extension, which is also IS, is N primary. And apart from this, we have this result that there is R comma M is Noetherian local ring. Then I contains a system if and only if radical of I is equal to M. Okay, this is the result. So once we get that, so since this here also, so if I contains system of parameters of R, then extension of I contains system of parameters of this N. Okay, is this clear? This what I wrote here. R comma M is an Noetherian local ring. Then I contains system of parameter if and only if radical of I is a maximal ideal. I mean, you can check this. And I mean, this clearly follows from the result which we had early. Not clearly, with some work from what we had earlier. That if A1, A2, An is a system of parameter, then dimension of R mod there is A1, A2, An, M is equal to 0. So this A1, A2, An, M must be contained in some. It should have height is equal to M, and those elements must be contained in some maximal ideal whose radical will be this maximal ideal. I mean, it needs some work, but it is doable. Okay, and I mean, these results which I wrote here, it is important. Where did I write it? I think, okay, wherever I wrote this, but I just want to say that if an ideal contains system of parameters, its radical will be a maximal ideal in a local ring. Okay, so I hope this much is clear for now. And remember this result because this is important. Okay, let me just star mark it. Any doubts here, like what we did here, at least for the argument of the that n being I extension of I being n primary, is there any doubt in that argument at least? It only requires the contraction properties and the radical follows the inclusion and so on. Okay, no doubts. Great. Then I will move to next question quickly. So question 5. Just a second. Yeah, this true or false again. So let Q be this Q be in M spec of ZX. Then there exists two irreducible polynomials f comma g such that Q is equal to f comma g. And any guesses here whether this is true? Or false? So when they are saying that this f and g are reducible polynomials, I mean, they are not considering them to be a constant. Okay, let us write it here. There exists two non-constant. Let me write. So any guesses whether this is true? Do we know how the elements of maximal spectrum of ZX look like? Okay, so consider this Z inside ZX. Okay, so let M be in M spec of ZX. Then M contraction will be some prime P in Z, right? The M contraction is M intersection Z, which is non-zero. Okay, I mean, so this M contraction will be some prime ideal P in Z, P in spec Z. Okay, so then M contraction is actually, let me write this again. It's some P prime number. So since we are considering this inclusion here, this P is also contained in that M contraction. Sorry, this ideal M which we started with in. So when I start with this, I mean this element P is in M contraction. So I'm again going back to my ideal M with the inclusion in ZX. Then there's this element P here. also belong to this maximal ideal M, which we started in this M spec Z X. Okay, so when I quotient it by this element M, there exists some H non-zero in Zx such that degree of H is greater than equal to 1 and H is non-constant. Because once I go modulo Zp, the quotients becomes, I mean, so let me write this. If when I go modulo P, this is isomorphic to this Zpx. Okay, so the coefficients are all invertible in that case. So this Z has to, this H has to have at least degree 1. Because in Zp, if I take any constant element, it is unit. So there exists some H non-zero in Zx such that degree of H is 1 and H is non-constant, and this H belongs to this M. M, again, the one I started here in maximal spectrum of Zx. So therefore, if this H is of this form, F1, F2, Fn, En, then this Fi belongs to M, okay, where this Fi is irreducible. When I started with this H could be any polynomial, okay? I cannot conclude there itself that this H has to be irreducible element. But when I go, when I look at its primary, its decomposition, since Zx is factorization domain, I look at its factorization and see, consider this irreducible element Fi. Okay, so since M is maximal ideal and hence prime ideal, this each Fi also belong to my ideal M. Okay, so therefore this P comma Fi contained in this M. But this is maximal, okay? Because now this Zpx is PID, and in that case, this Fi is generated by this single element and so on. So, I mean, this is maximal ideal, and this, therefore, this M is P comma Fi. So, this is constant plus some irreducible element F. Let me write this. F is irreducible in this Zpx, okay? So maximal ideals, so this is the description of maximal spectrum of Zx. So it is ideal generated by P comma F, where this P is a prime in Z and this F is a uh, reducible I element, reducible polynomial in Zx. Okay, so this expression where this F and G were non-constant polynomial, non-constant irreducible polynomial does not hold. Okay, because these are the only types of polynomial which are maximal in Zx. You can check that. I mean, we also saw it through some argument, but I hope this is clear. This is the form of M spec Z, Zx. Okay, and we use that to conclude that this is anyway not true. Is this okay? I mean, and this thing here actually needs some argument, okay? Needs some verification. Okay, I mean, when we start with some maximal ideal in ZXY, its contraction will always be some prime ideal and not uh, zero ideal. I mean, if it is a zero ideal, then what will happen? So that, I mean, then in that case, this M will be generated by, so this M will have elements of this form, right? X into some fx. Because when I substitute 0 in the x, I'm always getting 0 and something of that sort. And in that case, this M will be some ideal generated by x and which is not maximal. Okay, if both the elements are like x in are of the form x into something, then their coefficients will, sorry, then when I substitute x is equal to 0, they will give me 0 and it will no longer be maximal ideal because x we know is not maximal ideal because x is contained in ideal generated by x comma 2 in zx. Okay, so I mean, this is not very good argument, but just to get an idea. Is this okay? Please check this one. I'm writing this. Please check this. That contraction of maximal ideal from Zx. I mean, it will always be some prime ideal. Sorry, I mean, it will always be some P ideal generated by P, or it will always be non-zero ideal. But why it will be always a non-zero? You have to check that because anyway we know that maximal ideals of ZX are of this form. So it has to be some prime. Otherwise, this won't make any sense. But just by starting with the fact that we are considering one maximal ideal in ZX and we are contracting it, and that ideal is always a non-zero, showing that needs some work. And I hope you all can do that work. If not, please raise question in discussion forum and we will see. Okay, so let's move to next question. Again, true or false. So let R be Noetherian ring and I comma j are ideals. So R comma j are just ideals in I comma j are ideals in R. Then they are saying that height of j in R is at least height of this j plus I quotiented by I in R mod I. So when they are writing this j plus I mod I, they are just saying that so I and j are ideals in R, then height of j in R is at least height of j in R mod I. So when I say height of j in R mod I actually consider this. Okay. I mean, I hope you understand this is just because j actually need not contain the ideal I itself. So just to make sense of height of j in R mod I, we need to consider this j plus I. Okay. Even in earlier cases, when we were looking at height of x in xz, comma yz and ideals of those sort, we were actually considering the height of ideal, that element x comma the entire generators of those ideal I. That's what this mean here. I mean, I hope you understand what this means. This is just very bad way, but this is height of J mod I. If you understand what I mean, you can just ignore what I just said and we can move to the next question. So in short, what they are asking is, not next question, we will move to the solution. So what they are asking is that height of J in R is at least height of this J plus I quotiented by I in R mod I. This is the question. And they are asking this whether this is always true or not. So any guesses here that whether this will always be true? At least the intuition, what do you think? Whether this is true or not? Or any, because anyway, height of J is in R and we are going quotient with I and then looking at height of J in R mod I. So will this always be true? Okay, so actually this is not true because it might look because we are going quotient by I and so the height is reducing. Sorry, we are kind of omitting the ideas contained in I when we look at the quotient ring R mod I and so on, and we have this ideal J. But that is not true always. So let us consider this ring R is equal to K X Y Z quotiented by this X Y X Z. Yes. And this IB ideal Y comma Z in R and JB, let me write this small and this small and this X in R. Okay, so ideal Y and Z in R. So when I write this ideal Y and Z in R, it is ideal, it is ideal generated by this Y plus, let me call this ideal I, Y plus I, not I. Some ideal. What to do? Yeah, Q, let me write it Q. Z plus Q, we will change it or we won't even, or let me write this grothic A. IA, comma, Z plus A. And here this ideal is X plus A. Okay. So we are in this R. So we have to check this height of J in R. Okay. So height of J in R is looking at the dimension of R mod J. Okay. So height of J is, let us first calculate dimension of R. Dimension of R is what? The minimal primes here are X and Y comma Z. So X contained in XY comma XZ. So dimension of R is at least 2, right? And dimension of R mod I is what? Dimension of KXYZ quotiented by XY xz quotiented by this ideal generated by yz quotiented by xy comma xz. And when I write this, I actually mean this is dimension of this k x y z quotiented by this xy xz xy xz, right? Yeah, xy xz y comma z. D, is this okay? This is actually dimension of kx comma y comma z. Since y and z are here, we get this, and this is dimension of just kx, which is 1. So dimension of r mod I is actually 1. Now similarly, dimension of r mod j is similar to this. I'm just writing it here quickly. Kx, y, z quotiented by j was my x. So it is x comma xz comma yz. So this is dimension of xz comma xy comma xz. Dimension of kx, yz. I mean, these are just calculations, so nothing much to explain. And we are in monomial ideals, so not very difficult to see what is happening here. Still, if you have any doubt, so this is true. Okay, so I have this dimension of r mod j is 2 and dimension of r mod I is 1. So I want to check the height of this r mod j. Height of this r mod j is height of this x comma x y comma x z quotiented by xy comma xz, right? And that is height of this ideal generated by x in xy comma xz, which is 0, right? Because x is a minimal ideal here, and the just a second. Yeah, so x is a minimal prime here, right? So height of some ideal is what? It is minimum height of, let me just write here, is minimum of height of j such that j, very bad notation, a, yeah, a contained in I. So x is the ideal which contains, height of this is just 1 or 0, okay? I mean, I hope you understand. The minimum of height means this is just x here containing the, I mean, we have this chain x comma xy comma xyz, but we have to check the minimum of all those height, and this a is prime. Let me write this p. P is prime. So x is a prime ideal, which is also minimal prime, contained containing this xyz. So therefore, and this is the only chain here, p0. So therefore, height of this j in R is 0. Is this okay how the height is 0? Because x is the minimal prime whose height is 0 in R, which is also a minimal prime containing j. So height of j is a 0 because height of minimal prime containing this j, which is x, and height of x is 0. So that's it. I mean, height of this j is actually 0. So now I have some example where height of this j is 0 here. So if I show that this height of I plus j quotiented by I is non-zero, then I'm done, right? So now I have to check height of this height in R mod I. Okay. Height of I plus j quotiented by I. So height of, please bear with me because I have to write all these expressions. Xy, xz quotiented by this ideal generated by x, xy, xz. Now this ring is different than this ring, okay? This was in R was quotient by that ideal A, and this is now we are looking at R mod I. R itself is a quotient ring, and we are now looking at the quotient ring of a quotient ring. I hope this is not very confusing, and it is not actually, because we are just working with this nice monomial ideals. So this is just x comma y comma z and quotiented by this x. So this is height of this ideal y comma z. Is this clear how we are getting this? I mean, these two are isomorphic here. Mm, Let me just write this. These two are isomorphic rings. These two are isomorphic. This second isomorphism. Second or third. Yeah, this is second isomorphic. No, not second, third, I guess. Third isomorphism. And this xyz quotiented by ideal generated by x is just ideal generated by yz. And we know that height of this is at least 2, right? Because we have this y, sorry, in R mod I. This y contained in z, y contained in yz, and z contained in yz. So, therefore, height of this R I plus j is 1. Is this okay? Any doubts here? Height of this ideal yz is 2. Height of this height of this R mod I yz is 2. This is the only thing. Height of this is 2. Sorry, height of this is 1. This xyz is this height of in y comma z. Because we are going quotient. Height of this ideal is 2 here. Okay, height of, let. Sorry, 1. Because I have this y contained in y comma z. This is my P naught, this is P1. Similarly, I can take this. And just a second. Yeah. So, therefore, height of this x, which was 0, is less than height of this x plus y comma z quotiented by x, which is 1. Sorry, 1. So our question was, does this always hold? So this is not there. Height of this ideal y comma z is 1. Okay. I mean, is there any doubt here? Using this. Okay. So because of this, I think we missed this earlier, but height is, this is 0, this is 1. Height is 2, sorry, height is 1 of this ideal. Just a second. Yes. Okay, so I hope this is okay. So let us move to next question. That again we have this given condition that let I be a homogeneous radical ideal, okay, of, now we are in complex plane cxyz of height of height, just a second, let me check of height what. Of height 1. Okay, it is ideal of height 1, and we have to check the true or false that z of I contained in C cube. So now these are zeros of ideal I is the union of planes through origin. So Zi is set of all zeros in C cube and of this ideal I, and I is a homogeneous radical ideal of height 1. Okay, so I has height 1. So let I be this. So we have to check whether this is true or not. That always if I have ideal of height 1, then zeros of that ideal are always union of planes passing through origin. That's the question. Okay, so this is not true actually, because we can generate ideal of our kind such that its zeros need not be plane passing through origin. Okay, when we have to generate a zero set of a polynomial, I mean, we have some kind of liberty there. Okay, so let I is equal to xy, I mean, not always, but in most of the cases, xz comma yz. This is homogeneous, okay? It's homogeneous ideal, both of degree 2. And we can also check that this is also radical ideal, because I is what? It is x comma y intersection z. So this is, just a second. This is intersection of two prime ideals. So prime ideals, therefore I is radical. I mean, or we can directly check that if I is radical ideal, because intersection of two prime ideals and so on. So I has this decomposition x comma y intersection z. So z of I is actually z of x comma y union z of z. So this zeros, let me just cross this. This we saw earlier lectures, how in Zariski topology, how the zeros and varieties were. So this we know. So zeros of ideal, I mean, if you remember, we also solved this kind of equation exactly to find the how zero set of a ideal look like in C cube. I mean, it was the similar kind of question, and we know that if it is union of z of minimal primes, if you remember this, z of I is equal to union of z of p. P belongs to min I. If you remember, we have this. Here, this I itself is the intersection of two prime ideals, which are also minimal. And so z of I will be this. And this corresponds to z axis. And if you look at the zeros of this, it corresponds to xy plane. Okay, so zero of, if I want to show it in the this, yeah. So if this is my x, y, and z, then let it be. Then this x is one of the zero. This belongs to zero set, and also this xy plane, the entire xy plane. Okay, so this xy plane here, along with this z, actually gives me the zero set. And this is definitely not not the union of planes passing through origin, okay, because we have as z-axis belongs to z of this I. Okay, any doubts here? This z-axis belongs to 0 of this I. Is this okay? This xy plane along with this z-axis is the zero set, which is not of the form which is asked to us, the union of planes passing through origin. I hope this is okay. I mean, we have to use only this, the fact from previous lectures, to look at the zero set of a polynomial, zero set of ideal. So this is a bit lengthy, but let us see how quickly we can do this. So given that Rm is, let R comma M be again Noetherian local ring, and let M be finitely generated R module. Then let x1 to xs be in this M. Okay. The maximal ideal here and this M is finally generated. So see, this x1 to xm are elements from the ring R in maximal ideal of ring R, such that this M quotiented by x1 to xsm has finite length. I hope you remember what finite length means. We will again. Then we have to show that this annihilator M of M plus this x1 to xs is M primary. This is question from this unsolved or practice problem which are provided to you. Okay. So let us give notation. I is equal to x1 to xs, and we have that lambda r of I mod, sorry, M mod Im is less than infinity. So given for this I and this I is contained in M. Okay, this much is clear, right? I'm just giving notations to this A1, x1 to xs, which were element of M. I'm just writing them in ideal form. And this M quotiented by Im has finite length. That's what I have written here. So let this N be an R module. Then we claim that, now this is a general statement which I'm trying to prove here, that if N is an R module, then we claim that lambda R of N less than infinity implies support of N is M. And the moment I have this R M mod Im has what I can say. Yes, M mod Im has finite length. This will imply the support of this M mod Im is just this maximal ideal M. And we proved earlier that the system of parameter is actually the radical of that ideal is always be in M. Sorry, what I said. The system of parameter of a given ring, if I is generated by system of parameters, then radical of I will be in M. The system of parameter is contained inside radical of those elements is contained inside the M, and so on. I mean, if you remember, we did that earlier. Using that argument, we can conclude that this annihilator of M plus x1 to xs is M a primary. I mean, we will check that again. Okay, so let us start with that we know that N has a filtration. Okay, so the moment we say that the length of N is finite, then N has a filtration. That's the definition of length of some module. So we have this filtration of this form. This N is contained in N1, contained in some NR, which is 0. Okay, so we are actually considering this finite length to be R. Then, and this filtration is such that N I plus 1 quotiented by Ni is isomorphic to this R mod M, which is simple local ring. Okay, so this implies that this annihilator of N is contained in M because of this first step. Because this Ni plus 1 quotiented by Ni is isomorphic to R mod N. Okay, so this associated prime of this N is contained in M. Okay, so but M is the only ideal here. So associated minimal primes are subset of associated primes. So we also have this. So this implies that support of N has to be M, okay? And therefore, this, I mean, it is using many of the results which are actually this. You can see the using the results from lecture. Okay. So we got this, that support is just single element here. And so again, we are now in lambda r m mod I m less than in is finite. Then support of this m mod I m is also just this singleton m. Okay, and what is support of this m mod I m? It is P in spec R, the definition I'm writing here, such that MP mod IPMP is 0. When I write this, these are localization. Okay, this localization of M and I both with respect to this prime ideal P. Okay, and when I do the localization with respect to prime ideal, the multiplicative set is actually complement of that prime ideal. Okay, and so this is what? This is support of M intersection V of I, right? Because I want this to be non-zero. So when this will be non-zero? When this P is not a zero set, I mean this, what I can say, this, let me write this. This, if I have this, then this IP, it will be RP, right? The last time the argument which we gave. When I have localization, that ideal should not be intersecting with my prime ideal. Okay, so when I look at the prime ideals in a in localization, those ideal should not be intersecting with the my prime P, because if they do, then we are inverting those elements and so on. So I mean the 2 and 3 case which I proved last time. So remember that. So if this is the condition, then IP will be is equal to RP, and then this support of M will be just support of annihilator of M. This you can check, okay? This isomorphism is always there. Intersection V of I. For this to be non-zero, we have to have these two conditions. This MP must be non-zero and this must be non-zero. This entire thing must be non-zero. For this entire thing to be non-zero, it should satisfy this condition, because if this blows to the whole entire ring, then we are not getting what we wanted. The support has to be non-zero. Okay, there are two conditions which needs to be satisfied here. One of them gives us this and other one gives us this. Please understand this. And therefore, this is what? This is V of annihilator of M, right? You can also check this. Intersection V of I. But when I have this, this is the property which I have. The intersection gives me the addition here. And this is nothing but support of R mod annihilator of M plus I. So therefore, support of, but we already know support of this is actually M. So therefore, this radical of annihilator of M plus I is actually this M, that is this annihilator of M, which we started with, plus this x1 to xs, which was my I, is M primary. Is this okay? I mean, we have used many things here to arrive at this conclusion. But you can check this inequalities. I mean, we got this using this condition here, and annihilator, not annihilator, it's associated prime, sorry. I said associated prime, but I wrote annihilator. No, it's associated prime of n will be contained in M. When I write this, I mean this. Because this is simple local ring. Okay. Any doubts here? And then associated prime, this is like, we have this minimal of n contained in associated prime of n, which is contained in this M. And then is okay. And then support will be always be contained in this. So support will be this M. And therefore, so claim proved here. And using the claim, we get that support of M mod M quotiented by IM is this M. And we just followed the definition, like how, sorry, support of this M mod IM is related to support of this. And then just by definition, we get that. I mean, you have to go through, I guess, notes to understand all the results used here. Okay, not only notes, but also there are results which are used from the unsolved exercises or not unsolved, like the non-graded assignments which are provided to you every week. So there are many results there. Those who have not yet gone through those, please go through it, because it contains many more questions like what we are asked in assignment, and those also explains things in depth and so on. So please go through those, and if you have any doubts, please let me know. Is this okay? Okay. So if you have any doubt, please raise it in the discussion forum. And apart from this, since we are already over the time, I think we can stop here. Is that okay? Or you want to ask anything? Okay. So thank you. We'll meet next week.